All right, in this explainer, we're going to build an atom from the ground up. And in the process, we're going to uncover some of the strange and really beautiful rules that govern, well, everything.
You know, you probably learned about the atom as this tiny little solar system, right? A nucleus in the middle with electrons just orbiting like planets. But it turns out the reality is so much weirder and way more fascinating than that.
So let's dive right into the architectural blueprint of matter itself.
Here's the game plan. We'll start with the absolute basics inside the atom. Then we'll figure out where the electrons actually live, their address, so to speak. We'll look at the bizarre shapes of their homes, learn the rules for how they fill those homes, and finally, see what happens when atoms bend those rules in their search for stability.
Okay, first things first. Let's meet the three fundamental particles that make up every single atom in the universe.
Right at the heart of the atom, in the nucleus, you've got your positive protons and your neutral neutrons. These guys are the heavyweights. They make up almost all of an atom's mass. Then, buzzing around the outside, you have the electrons. They've got a negative charge, and they are incredibly tiny, almost 2,000 times lighter than a proton or neutron. Now this is where it gets really interesting. When these particles fly through an electric field, their opposite charges make them bend in opposite directions. But look at that difference. Because the electron is so incredibly light, that same electric force yanks it way, way farther off course than the big, heavy proton. So where do these tiny electrons actually live? It's not just a random cloud, not at all. It's actually a highly organized system, almost like a cosmic address for each electron. And this address has three parts. First, you've got the main energy level, or the shell. You can think of this as the country. It tells you roughly how far the electron is from the center. Inside that country, you have subshells, which are like the state. And finally, you have the atomic orbital, which is the specific city where the electron is hanging out.
Now here's the crucial point, and it's a bit of a mind bender. An orbital isn't a fixed path. It's not like a train on a track. It's a cloud of probability. It is the specific region of space where there is a 95% chance you'll find that electron at any given moment. It's all about statistics.
And believe me, these probability clouds can get really, really weird. Let's take a look at the actual shapes of these electron homes. The simplest one, the s orbital, is just a perfect sphere of probability centered on the nucleus. Okay, easy enough. As we move up in energy, we get to the p subshell. This contains three separate orbitals. Each one looks like a dumbbell, and they're all perpendicular to each other, pointing perfectly along the x, y, and z axes. And now for the d orbitals. This is where the shapes get even more complex. Most of these 5 orbitals look kind of like 4-leaf clovers, with their lobes of probability sitting right between the axes.
But there's always an odd one out, right? Meet the z-squared orbital. It looks totally different from its siblings. It's got the 2 main lobes like a dumbbell along that vertical z-axis, but then it has this incredible ring, a donut really, of probability right around the middle. It's just a beautiful, strange exception.
So we have all these amazing, different orbital shapes. How do electrons actually decide which one to live in? Well, it's not random. There are 3 key rules that we have to follow.
The first rule is called the Aufbau principle, and it's simple. Electrons are lazy. They always take the lowest energy spot available. They start at the bottom and fill their way up. But here's the catch. Notice how the 4s orbital fills before the 3d orbital? Yeah, sometimes a shell with a higher number can actually be lower in energy. It's a fun little quirk. Next up is Hund's rule, which I like to call the empty bus seat rule. You know how when you get on a bus, you take an empty row before you sit next to a stranger? Electrons do the exact same thing. Within a subshell, each orbital gets a single electron before any of them are forced to double up. It minimizes repulsion. And finally, the Pauli exclusion principle. This one's a big deal. It says that if 2 electrons must share an orbital, they cannot be identical. They have to have opposite spins, which is a fundamental quantum property. We show this with those half arrows pointing in opposite directions, one up, one down. They have to oppose each other to coexist in the same tiny space. Okay, so we've got our rules. But in science, the most interesting things often happen when the rules get, well, bent a little bit, all in the name of stability. Let's look at the element chromium. It has 24 electrons. Now, if we just follow the Aufbau principle exactly, this is what we would predict. We'd fill up the 4s orbital with 2 electrons, and then put the last 4 into the 3d orbitals. Seems straightforward, right? But that's not what happens in nature. When we actually look at a chromium atom, we see something different. The atom takes one of its electrons from that lower energy 4s orbital and promotes it up to the 3d orbital. Why on earth would it do that? It seems to break the rules we just learned.
And here is the secret. It's all about finding extra stability. It turns out that there is a special, super stable, low-energy state that comes from having a subshell that is exactly half full, like this 3d5 configuration, or completely full. The atom is actually willing to break the standard filling rule just to achieve this more stable, more symmetrical state.
And this idea, this relentless drive for stability, for the lowest possible energy state, that's not just some weird quirk for one element. That is the fundamental force driving all of chemistry. It's the reason atoms bond, the reason they react, and the reason they form the entire complex world we see all around us.